Humanity's next home may not be a planet at all. It could be a colossal, self-contained world of our own making, floating gracefully in the silent ocean of space. This is the promise of the ONeill cylinder, a vision so ambitious it redefines our place in the cosmos. By the end of our journey, you will grasp the complete blueprint for building these artificial worlds, from their scientific foundations to their societal soul. We will uncover how a simple question from a physicist sparked a movement and confront the staggering challenges of creating gravity, weather, and community inside a spinning can. What does it truly mean to become a species of world builders? That question was a spark in the intellectual dark. It was 1974, and while the world was still marveling at footprints on the moon, a physicist named Gerard K. ONeill posed a challenge to his students at Princeton University. He asked them to think not about visiting other worlds, but about building new ones from scratch. The assignment was not science fiction, it was an engineering problem, and the answer they arrived at, after rigorous calculation, was startling. A planetary surface, with its deep gravity wells and limited space, might actually be a terrible place for a civilization to grow. The best place for humanity's future, they concluded, was in free space itself, inside enormous manufactured habitats. This was the genesis of a vision that would consume ONeill's life. Gerard ONeill was a unique blend of dreamer and pragmatist. He held a deep concern for the long-term survival of our species, seeing Earth as a fragile cradle. He witnessed the energy crises and environmental discussions of the 1970s and recognized a fundamental tension. An expanding civilization requires vast resources and energy, but harvesting them from a single planet comes with profound costs. His solution was to look upward to the limitless solar energy and raw materials of the asteroid belt. But you cannot mine asteroids from a desk on Earth. You need a home base in space, a place where thousands, then millions, could live and work permanently. This was the practical heart of his dream, a way to preserve Earth's biosphere while allowing humanity to flourish without limits. He channeled this vision into a seminal work, a book titled The High Frontier. Published in 1977, it was not merely a proposal, it was a detailed blueprint. ONeill filled its pages with precise physics, engineering schematics, and economic models. He calculated rotation rates for artificial gravity, designed radiation shielding from lunar soil, and sketched out internal landscapes with mountains, rivers, and towns under a simulated sky. He presented space settlement not as a distant fantasy for the far future, but as an achievable goal for the next few decades, a logical next step for a species that had just learned to leave its home planet. The book captured the optimism of the post-Apollo era, a time when it seemed humanity's trajectory was irrevocably pointed toward the stars, and it sparked a movement. The High Frontier became a manifesto for a generation of engineers, scientists, and forward thinkers. It led to influential NASA summer studies at Ames Research Center, where teams of experts refined the concept. It inspired the founding of the L5 Society, a grassroots group dedicated to promoting space colonization. ONeill himself became a tireless advocate, debating skeptics and painting a compelling picture of a hopeful, off-world future. His legacy is not a single invention, but a complete intellectual framework. He gave us the permission to think big, to see space not as a void to cross, but as a place to live. He provided the first rigorous answer to the question of how, transforming a dream into a series of engineering problems waiting to be solved. To understand the cylinders we might one day build, we must first understand the clear, calculated vision of the man who dared to draw their blueprints. That vision rests on a few elegant yet powerful physical principles. The elegance of ONeill's vision lies in solving profound problems with simple physics. To build a home in space, you must first answer a basic human need, the need to stand up, to walk, to feel the reassuring pull of a world beneath your feet. Long-term weightlessness presents a serious challenge to the human body, leading to loss of bone density, muscle atrophy, and other health issues that make permanent life in zero gravity impractical. The cylinder's solution is both beautiful and straightforward. It creates gravity not with mass but with motion. The entire structure rotates around its long central axis, like a rolling pin spinning in the void. This rotation generates a force called centrifugal force. If you have ever been on a merry-go-round and felt yourself pushed outward as it spins, you have felt a version of this force. Inside the cylinder, this outward push becomes your new down. The inner curved surface of the cylinder becomes the ground, and everything and everyone inside is gently pressed against it, creating the steady, familiar sensation of gravity. The engineering is a careful balance. The strength of this artificial gravity depends on two things: how fast the cylinder spins and how wide it is. A smaller habitat would have to spin very quickly to achieve Earth-like gravity, which could cause dizziness and disorientation for its inhabitants. But ONeill's design calls for a cylinder several kilometers in diameter. At that immense scale, it only needs to complete one full rotation every minute or two to perfectly mimic the gravitational pull we experience on Earth. This slow, stately spin would be almost imperceptible to those living inside, except for two subtle effects. If you dropped an object, it would appear to curve slightly as it fell. And if you looked far down the immense interior valley, the distant landscape would seem to rise up and curve over your head, a gentle reminder that you are living inside a crafted world. This principle of rotational gravity is not science fiction. It is Newtonian physics, demonstrated in laboratories with small centrifuges for decades. It is the foundational trick, the first and most important act of world building that makes everything else possible, from flowing rivers to stable buildings to the simple, healthful act of a morning walk in a park under an artificial sky. But creating a stable, Earth-like gravity is only the first act of engineering. A single giant cylinder spinning alone in the void would face a hidden, powerful force of its own making. This is the challenge of angular momentum, a fundamental property of any rotating object. Think of a figure skater pulling in her arms to spin faster, or a child's top wobbling as it slows down. A solitary ONeill cylinder would behave like a colossal gyroscope, stubbornly resisting any attempt to change its orientation in space. This rigidity presents a practical nightmare. To sustain life, the habitat must maintain a fixed angle relative to the sun, its primary source of energy and light. If it could not be pointed steadily, its solar collectors would fail, and the carefully balanced interior climate would plunge into chaos. A habitat that cannot aim itself is a world doomed to drift into darkness. Gerard ONeill's elegant solution to this problem is a masterpiece of mechanical symmetry. He proposed not one cylinder but two. These twin habitats would be connected at their ends by a sophisticated central bearing system, a kind of cosmic axle. Crucially, they would spin in perfect opposition to one another. While one cylinder rotates clockwise, its twin rotates counterclockwise. This counter-rotation is the key to stability. The angular momentum generated by one cylinder is precisely cancelled out by the equal and opposite momentum of its partner. The net result is zero. This means the entire paired structure as a whole loses its stubborn gyroscopic resistance. It becomes nimble, able to be slowly and easily turned by relatively small thrusters to keep its sun-facing side aimed at the light, just as a sunflower tracks the sun across the sky. For the inhabitants inside each cylinder, this grand balancing act is invisible. The experience within one of these spinning worlds remains unchanged, a steady, gentle gravity pressing feet to the grass on the inner curve. They would be unaware of their twin worlds spinning the other way just a short distance away, connected by a non-rotating central hub that could serve as a docking port or a zero-gravity observatory. This paired design transforms a wobbly, uncontrollable top into a stable, steerable arc. It is a non-negotiable cornerstone of the vision, the difference between a precarious experiment and a permanent home. And by solving the problem of stability, it directs our attention to the very source of that stability's purpose, the brilliant, constant flood of energy from the sun that makes the entire endeavor possible. That stable, steerable arc needs a constant, colossal heartbeat of energy. An ONeill cylinder is not a passive vessel. It is a living machine, a breathing world that demands immense power every single second. It requires electricity to purify air and recycle water, to run factories and farms, to power homes and transport systems. It needs light to flood its interior landscapes, driving photosynthesis in its plants and regulating the circadian rhythms of its inhabitants. This staggering demand finds its answer in the most abundant, reliable power plant in our solar system, the sun. And in the silent vacuum of space, we can harvest that energy with an efficiency impossible on Earth. Here, our atmosphere scatters and absorbs sunlight, and night falls every 12 hours, cutting off the supply. But in orbit, the sun shines 24 hours a day, unimpeded by clouds or air. To capture this endless stream, the cylinders would be accompanied by vast, delicate structures, solar collectors on a scale we have never built. Picture mirrors, kilometers across, made from foil-thin, reflective film. These are not heavy glass panels, but ultra-lightweight sails, precisely angled to focus sunlight where it is needed. Some of this concentrated light would be directed onto photovoltaic cells to generate electricity directly. But the most elegant application is for illumination itself. Running the entire length of each cylinder would be 3 immense, longitudinal windows. Outside, the great mirrors would be positioned to reflect a steady beam of sunlight directly through these panes. This is how the cylinder gets its sky, not from bulbs or screens, but from actual, focused sunlight, giving the interior a quality of light indistinguishable from a clear day on Earth. To create a familiar day-night cycle, the mirror arrays would be carefully orchestrated. They would slowly tilt away, allowing the windows to darken into twilight and then night, mimicking the comforting rhythm of sunset and sunrise. This cycle could even be programmed for longer nights in winter or adjusted for shift workers, giving the community control over one of nature's most fundamental patterns. The engineering behind these systems pushes the limits of material science. The mirrors must be incredibly light to be launched or constructed in space, yet sturdy enough to hold their precise shape against the subtle push of solar radiation. The window glass, likely a layered composite, must contain the habitat's atmosphere while withstanding micrometeoroid impacts and decades of solar radiation. Distributing the power and light internally is another layer of complexity, requiring a resilient grid that can operate flawlessly for generations. The scale of this power infrastructure is monumental, a symphony of physics and engineering playing out on a cosmic stage. Yet overcoming this challenge does more than keep the lights on. It unlocks the possibility of creating something far more delicate and alive, a self-sustaining bubble of biology within the mechanical hull. The sheer scale of the materials required is almost beyond comprehension. We are not talking about thousands of tons, but billions of tons of steel, glass, soil, and water. Launching even a fraction of that from Earth would bankrupt nations and exhaust our planet's resources, a self-defeating exercise for a project meant to preserve our home. This is the first and most fundamental economic wall any space settlement plan hits. To build cities among the stars, we must learn to live off the cosmic land, to become builders who use the materials the universe has already provided. This shift is known as In-Situ resource utilization, and it transforms the entire endeavor from a supply chain nightmare into a plausible, even elegant industrial process. Our solar system is not an empty construction site. It is a warehouse filled with precisely the raw materials we need. Two sources stand out as our primary suppliers: the Moon and the asteroids. The Moon's surface, covered in a layer of dust and broken rock called regolith, is rich in oxygen, silicon, aluminum, and titanium. It is essentially a quarry of pre-processed construction materials, lacking only an atmosphere and water to make extraction easy. Even more tantalizing are the near-Earth asteroids, rocky or metallic bodies that drift close to our planet's orbit. Metallic asteroids are essentially mountains of iron, nickel, and cobalt, along with precious trace elements like platinum and gold. Carbonaceous asteroids are packed with water ice, carbon compounds, and clays, the very building blocks for soil and life support. The vision, then, is one of cosmic industry. Picture fleets of autonomous robotic miners, not unlike the heavy machinery in terrestrial mines, but designed for the airless, low-gravity environments of the Moon or a captured asteroid. These machines would scoop, sort, and process raw regolith or rock. On the Moon, one of the most compelling ideas is the mass driver, a long electromagnetic railgun built on the lunar surface. Because the Moon has no atmosphere and only 1/6 of Earth's gravity, it takes far less energy to launch material into space. Raw processed materials could be loaded into capsules and accelerated along this track, shooting them off the Moon on a precise trajectory to a construction facility waiting at a stable orbital point, like a cosmic loading dock. For asteroids, the strategy might involve nudging entire small asteroids into a stable orbit near the construction zone, or using advanced processing units to extract valuable materials on the spot and send only refined products. This is where the dream becomes tangible engineering, the moment when raw space rock is transformed. That lunar regolith, for instance, can be processed in orbital furnaces powered by focused sunlight. The intense heat can melt it into glass for windows and fiber for structural composites, or use chemical processes to extract pure metals for beams and cables. Water ice from asteroids becomes breathable oxygen and drinking water, and its hydrogen and oxygen can be combined to make rocket fuel, powering the very ships that run this new economy. This pivot from Earth-dependent to space-based manufacturing is the essential first leap. It means the first cylinder is built with immense effort and investment, but every beam and pane of glass produced afterwards comes from a growing, self-sustaining orbital industry. The construction site itself becomes a factory, and the factory becomes the foundation of a new economic sphere, one that finally unlocks the practical means to assemble our carefully designed habitats in the unforgiving quiet of the void. Building a world from orbit is a task of almost unimaginable patience. You have the raw materials, mountains of processed metal and glass now drifting at a cosmic construction yard. But how do you take these pieces and assemble them into a cylinder large enough to hold a river, under conditions where there is no ground to stand on, no atmosphere to carry sound, and every action has an equal and opposite reaction that could send a builder tumbling into the void? This is the second monumental challenge, orbital construction, and it demands a complete reinvention of how we build anything. The process begins not with a groundbreaking, but with a framework. The first task is to construct the massive central axle, the non-rotating spine that will connect the twin cylinders. This structure, likely a hollow truss of immense strength, becomes the stable backbone of the entire project. From here, construction would unfold outward in a carefully sequenced orbital ballet. Prefabricated segments, the curved hull plates that will become the cylinder's outer wall, would be maneuvered into place. But human workers in bulky suits cannot safely bolt these city-sized pieces together. The forces are too great, the precision too fine, the environment too hazardous. Instead, the primary workforce will be swarms of autonomous and teleoperated robots. Imagine a cloud of specialized machines, each with a specific purpose, moving in a coordinated dance. Robotic arms with advanced welding tools would fuse hull segments together, their movements guided by lasers and sensors to micron-level accuracy. Smaller spider-like drones would crawl across the growing structure, inspecting every weld and applying protective coatings. Larger robotic tugs, essentially space cranes, would ferry new segments from storage depots to the precise point of assembly. Guiding this symphony would be a hierarchy of artificial intelligence systems, managing logistics, preventing collisions, and adjusting the construction sequence in real time to account for any unforeseen issue. Human overseers would likely monitor the entire operation from the safety of a shielded control station, perhaps located in the central hub, intervening only for high-level decisions or complex problem-solving. The techniques themselves push beyond traditional manufacturing. One of the most promising tools is large-scale 3D printing in the vacuum of space. Instead of shipping pre-made beams, robotic printers could use metallic dust extracted from asteroids, melting it layer by layer with focused sunlight or lasers to print structural components directly onto the growing framework. This on-demand fabrication would drastically reduce the need to launch specific parts from Earth or even from lunar factories, allowing the construction project to adapt and use the most locally available materials. It turns the construction site itself into a factory. Coordinating this endeavor is a logistical nightmare spanning decades. Every bolt, every circuit board, every liter of coolant must be accounted for and delivered to the right place at the right time across millions of kilometers of space. The supply chain becomes a fragile lifeline, a constant stream of automated freighters shuttling between resource processing centers and the growing habitat. A single major delay or accident could set the project back years. This demands not just advanced robotics, but unprecedented levels of project management software and resilient, redundant systems. The stage for this grand project is not just anywhere in orbit. The ideal location is a gravitationally balanced point in space known as a Lagrange point, specifically L4 or L5 in the Earth-Moon system. These are regions where the gravitational pulls of Earth and the Moon create a stable pocket, like a gentle hilltop in the fabric of space. An object placed here requires very little energy to stay in position, making it a perfect parking spot for a decades-long construction project. This stable point would become the first true industrial park in space, a buzzing nexus of robotic activity where the skeleton of a new world slowly takes shape against the backdrop of the distant Earth. This metallic skeleton, however, is just a lifeless shell. The true magic and the next profound challenge is what happens inside, transforming this engineering marvel into a living, breathing biome. The skeleton of the cylinder is merely a vessel waiting for its soul. Within that vast, curved hull lies the true masterpiece of engineering, a complete living world. This is not a cramped spacecraft interior, but a sweeping valley, kilometers long, cradling rivers, forests, and towns under a ribbon of artificial sky. The goal is not survival, but vitality, to craft an environment so Earth-like, so psychologically nourishing, that its inhabitants forget they are living inside a machine. Achieving this means building a biosphere from the ground up, a feat of ecological engineering called a closed ecological life support system. Picture the most elaborate, beautiful terrarium you have ever seen, then scale it up to the size of a small country and make it absolutely perfect, because a single major failure could mean the end of everything inside. The foundation of this world is its soil. You cannot simply haul dirt from Earth, the quantities are impossible. Instead, engineers would create a custom growing medium, likely starting with processed minerals from lunar or asteroid regolith, rich in the essential elements plants need. This sterile mineral base would then be inoculated with carefully selected bacteria and fungi to create a living soil web, and mixed with recycled organic matter from compost. The plants chosen for this new Eden are not just for food, they are the lungs, kidneys, and heart of the habitat. Fast-growing crops like wheat, rice, and leafy greens would provide calories, while legumes would help fix nitrogen in the soil. Towering bamboo groves could offer rapid biomass for construction materials and oxygen production, but the selection goes far beyond utility. Gardens of flowering plants, stands of familiar trees like oak or maple, and even small wildflower meadows would be essential, not for eating but for the human spirit. Their presence maintains biodiversity, supports pollinators, and provides the profound psychological comfort of green, growing things, fighting the potential sense of confinement. Water is the bloodstream of this closed world. Every drop is precious and must be endlessly recycled. The system would mimic Earth's hydrology in miniature. Water evaporates from soil, plants, and bodies of water, rising into the atmosphere. Since there is no natural rain, the habitat's climate control system would carefully manage humidity, condensing this moisture on cooler surfaces or in dedicated condensers, purifying it, and then releasing it as gentle, scheduled precipitation over agricultural zones and wild areas. Rivers would flow from higher elevations, fed by these controlled systems, winding through the landscape before being collected, filtered, and pumped back to their sources. Lakes would act as reservoirs and recreational spaces, their levels meticulously monitored. The entire cycle, from a person's shower to the dew on a leaf, would be tracked and managed by a network of sensors and automated systems, a silent, constant ballet of renewal. Most critical of all is the air. The atmosphere inside the cylinder must maintain a stable pressure and a perfect balance of gases, primarily nitrogen and oxygen, with trace carbon dioxide for the plants. The plants, through photosynthesis, are the primary oxygen generators, but the system cannot rely on them alone. Mechanical backups, like electrolysis units splitting water into oxygen and hydrogen, would always be on standby. Carbon dioxide exhaled by people and animals would be scrubbed from the air and either fed directly to plants in concentrated greenhouses or processed chemically. Every molecule is accounted for. Even the smell of the air is a design consideration, a blend of soil, vegetation, and cleanliness, deliberately curated to avoid the sterile scent of a hospital or the metallic tang of a spacecraft. This biospheric engineering is the most delicate and continuous challenge of all. It is a dynamic, living puzzle where every part is connected. A pest outbreak in the wheat fields, a fungal bloom in a lake, or a glitch in the atmospheric processes are not isolated incidents, they are system-wide emergencies. The human residents would need to become expert stewards, a community of farmer ecologists monitoring the health of their world with as much care as they monitor their own. They are not just living in a habitat, they are an integral part of its metabolism. This intricate, beautiful bubble of life exists in stark contrast to the reality just meters away beyond the hull, where the absolute vacuum and lethal radiation of space wait. That thin barrier is all that stands between a thriving valley and oblivion, making its integrity and the systems that protect it the ultimate guardians of this crafted dream. That delicate bubble of life exists within a fortress, a shield against an invisible and relentless enemy. The space between worlds is not an empty void, it is a torrent of high-energy radiation. Cosmic rays, atomic nuclei traveling at nearly the speed of light, streak through the solar system. The sun itself can erupt in violent solar particle events, blasting out waves of protons that would deliver a lethal dose to any unprotected human in hours. On Earth, we live under a protective blanket, our atmosphere and magnetic field deflecting and absorbing these particles. An ONeill cylinder has no such natural defenses. It must build its own, and this requirement for shielding becomes one of the single most massive and defining elements of the entire design. The primary method is beautifully simple, brute mass. The principle is one of absorption. When a high-energy particle smashes into an atom within a thick wall of material, it collides, loses energy, and gets stopped. The thicker and denser the material, the better the shield. In the cylinder's design, this shielding is not a separate layer you bolt on. It is integrated into the very fabric of the world. The outer hull itself, likely a multi-layered composite of metals, provides the first line of defense. But the real shield is the landscape, the soil that forms the valley floor, the bedrock beneath it, the very mass of the world's infrastructure. All of it serves a dual purpose. Engineers calculate the required depth meticulously. To reduce radiation to safe, Earth-like background levels for a permanent population, you need a barrier with the stopping power equivalent to about 5 meters of solid rock or 1 meter of water. This means the layer of soil covering the interior landscape must be several meters deep, not just a thin veneer for plants. The mountains and hills sculpted into the interior are not just for beauty, they are strategic radiation barriers, their bulk protecting the valleys behind them. Even the water in the lakes and rivers adds to the shielding mass. This necessity directly shapes the cylinder's colossal scale and immense weight. It cannot be a lightweight tin can. It must be a solid, hefty shell, packed with material, which in turn drives the astronomical resource requirements we discussed earlier. The quest for effective shielding has spurred innovative concepts beyond simple mass. One visionary idea is to create an artificial magnetic field, a miniature version of Earth's magnetosphere. This would involve deploying enormous superconducting rings around the cylinder, generating a magnetic bubble that would deflect charged particles away, much like a force field in science fiction. While theoretically possible, the scale of such a system and the immense energy required to sustain it make it a technology for a far more advanced future. Another concept is active shielding, using charged plates or plasma to create an electrostatic barrier. These alternatives are alluring because they could dramatically reduce the needed mass of the habitat, making construction easier. But for the first generations of cylinders, the proven, passive reliability of mass shielding, of simply putting enough stuff between you and the cosmos, will be the trusted solution. This invisible fortress is the silent guardian of every breath taken and every step walked inside. Its design is a constant negotiation between safety and practicality, a reminder that the comfort of an Earth-like valley is maintained by an immense, quiet bulwark against a universe that is, in truth, profoundly hostile to unprotected life. This fortress, however, must also be a flexible, resilient home, capable of enduring not just radiation, but the unpredictable stresses of its own existence and the rare but inevitable emergencies of life in space. The air inside this world is a constant, gentle pressure, a life-giving force that also poses the single greatest physical threat to the entire structure. For every square meter of the cylinder's inner surface, Earth's normal atmospheric pressure exerts a force equivalent to 10 metric tons pushing outward against the hull. This is not a static load, it is a dynamic, relentless strain, compounded by the centrifugal force of the cylinder's own rotation, which adds its own massive outward stress. The structure must bear this combined burden not for years but for centuries without a single catastrophic failure. The integrity of this pressurized shell is what separates a living valley from instant, silent oblivion. To understand the challenge, think of a simple soda can. It holds its shape because the pressure inside and outside are equal. But in space, the outside pressure is absolute zero, a perfect vacuum. Our cylinder is like a soda can holding back an entire ocean of force, and it is spinning at the same time. The engineering solution lies in a combination of revolutionary materials and brilliant structural design. The hull cannot be a simple, solid wall of steel that would be impossibly heavy and prone to stress fractures. Instead, it would be a composite marvel, likely built from advanced carbon fiber polymers or, in a more futuristic scenario, carbon nanotubes. These materials offer a strength-to-weight ratio hundreds of times greater than steel, meaning they can withstand immense forces while remaining relatively lightweight, a critical consideration for something built in orbit. The design would resemble a geodesic sphere but stretched into a cylinder. Visualize an internal skeleton of immense, arched ribs and longitudinal spars, forming a rigid triangular grid. This gridwork, like the bones of a colossal whale translated into engineering blueprints, distributes the stresses evenly across the entire structure, preventing any single point from bearing too much load. The outer skin attached to this framework would be a layered composite, perhaps with a self-sealing layer to automatically patch tiny micrometeoroid punctures before significant air loss occurs. Managing the stress is an ongoing calculation. Thousands of sensors embedded throughout the hull would constantly monitor strain, temperature, and integrity, feeding data to central systems that could adjust the cylinder's rotation minutely or activate compensatory supports if a weakness is detected. Redundancy is woven into every layer. Critical sections of the hull might be double or even triple-walled, with the spaces between serving as utility corridors or additional radiation shielding. In the event of a significant breach, massive, rapid-acting airlock doors could slam shut, segmenting the cylinder into isolated pressurized zones to contain the damage and save the majority of the atmosphere and the population. This is the ultimate covenant of the ONeill cylinder, a promise written in carbon fiber and advanced polymers. The very sky the inhabitants look up to, the air they breathe, is held in place by a silent, continuous triumph of engineering. It is a testament to our ability to create not just shelters, but enduring, resilient homes, allowing us to turn our attention from the physics of survival to the human art of living, to explore what a society born among the stars might choose to become. The true test of this engineered world is not its physics, but its people. An ONeill cylinder is not just a machine, it is a society, a blank slate upon which entirely new forms of human life must be written. Its closed, curated environment forces a fundamental rethinking of our most basic social structures, from how we own land to how we govern ourselves. With a finite, precious interior landscape, the concept of private property as we know it becomes almost unthinkable. There would be no sprawling suburbs, no vast private estates. Instead, land is a shared, vital resource, the literal ground of everyone's survival. Urban planning evolves into a form of ecological and social gardening. We might see decentralized, village-like communities nestled into valleys or along terraced hillsides, each with its own character, connected by winding paths and light rail lines that follow the gentle curve of the world. Personal transportation would likely be quiet and clean, bicycles and small electric vehicles gliding along the inner circumference, where a short trip could literally take you around the world. The scale encourages intimacy with place, knowing your neighbors and the rhythms of your local biome, because every tree and stream is part of a shared life support system. This physical reality births new economic possibilities. With abundant, free solar energy and armies of automated systems managing infrastructure, agriculture, and manufacturing, the colony could edge toward a post-scarcity model for life's essentials. Food, clean water, shelter, and energy might be guaranteed fundamentals, not commodities. Yet this doesn't eliminate economics, it transforms it. The economy could shift toward trades based on creativity, information, specialized craftsmanship, and intellectual exploration. An artist's unique perspective, a chef's novel recipe using hydroponic ingredients, a programmer's elegant solution for the habitat systems, or a scientist's pure research could become the new currencies of prestige and exchange. Governance in such a transparent, interconnected environment would demand radical transparency and participation. With the survival of all so visibly linked to the health of the whole, decision-making would likely be intensely local and consensus-driven, perhaps facilitated by real-time digital platforms that allow every citizen to understand the systemic impact of policies on air quality, water recycling, or agricultural output. The legal framework must be built from scratch, confronting questions no earth-bound constitution ever considered. Who owns the rights to an asteroid mining technique developed in the colony? What are the rights and responsibilities of an artificial intelligence that manages a quarter of the food supply? The psychology of this life is its own frontier. Residents would live with a breathtaking panoramic environment, a valley that rises up and wraps over their heads under a sky that is a deliberate creation. This could inspire a profound sense of wonder and collective stewardship, a daily reminder of their extraordinary achievement. Yet, the same awareness could bring a sense of vulnerability, knowing your entire world is contained and maintained. Cultivating mental well-being would be as critical as growing crops, requiring ample green spaces, community rituals, and perhaps even virtual reality suites offering the illusion of boundless, wild earth landscapes to soothe the soul. This social blueprint reveals the ultimate ambition of the vision. It extends far beyond hardware into the very fabric of human life, and to weave that fabric together, to connect those village communities and sustain the flow of goods and ideas, the cylinder requires a circulatory system, a transportation network as innovative as the world it serves. Moving through this crafted world introduces a subtle, invisible hand. The cylinder's rotation, which creates its comforting gravity, also generates a phenomenon known as the Coriolis effect. It is the reason hurricanes spin in a particular direction on Earth, and inside a spinning habitat, it means that any object moving freely does not travel in a straight line. If you threw a baseball directly forward, it would appear to drift slightly to the side as it flew. If you dropped a marble from a high balcony, it would not fall straight down, but land a small distance behind its starting point relative to the spin. This is not a flaw, but a simple law of physics in a rotating frame of reference. For daily life, the effect is minor, a quirk to get used to, like learning to walk on a ship at sea. But it shapes the design of everything. Air circulation systems must account for it to ensure even distribution of warmth and fresh air. Water flowing in rivers would exhibit a slight, consistent curl. And sports would be reinvented. A long pass in a football game would require a new kind of instinct, and the arc of a basketball shot would demand recalibration. These adaptations become part of the culture, a shared physical language unique to life inside a spinning world. Yet the true test of mobility is not just inside one cylinder, but between them. Each habitat is an island in the orbital sea, and connecting them requires precision and grace. The ports for this inter-habitat travel are not on the curving landscape, but at the very heart of the structure, on the central, non-rotating axis. Here at the hub, the spin of the cylinder is almost zero. This is where spacecraft from other colonies, or from mining outposts in the asteroid belt, can dock safely and easily, without having to match the dizzying rotation of the main body. These central hubs become the bustling train stations of space, alive with activity. Shuttles and cargo tugs come and go, ferrying people, fresh food, specialized machinery, and data drives packed with news and entertainment. A traveler could board a sleek, zero-gravity shuttle at their home cylinder, float through a connecting tunnel to the hub, and then transfer to an inter-orbital vessel bound for another habitat thousands of kilometers away, perhaps one specializing in biotechnology or zero-gravity manufacturing. The logistics of this dance are complex. Approaching a rotating structure requires precise navigation, with docking clamps and airlocks designed to engage smoothly. The entire network would rely on strict scheduling and traffic control, a cosmic air traffic system to prevent collisions in the busy lanes between worlds. This vision points toward a future not of isolated cylinders but of a growing constellation, a circumterrestrial civilization of interconnected habitats. They could form trade alliances, share cultural exchanges, and support each other in times of need. One cylinder might focus on dense agricultural production, another on advanced research, another on recreation and tourism, each trading its surplus for what it lacks. This web of travel and trade cannot run on goodwill alone. It needs a powerful, sustainable engine, a practical reason to keep building and connecting. That engine is the promise of a new economic sphere, one that begins with supplying the basics of survival and expands to unlock resources of almost unimaginable scale. The airlocks and shuttle ports are not just for people, they are gateways for commerce. A habitat that merely consumes resources is a fragile, dependent outpost. But a habitat that produces valuable goods that trades becomes a resilient, growing node in a new economic network. The survival of an ONeill cylinder depends on this transition from consumer to producer, and its greatest asset is the very environment that surrounds it, the pristine vacuum and persistent microgravity of space. These conditions, harsh to life, are a perfect laboratory for industry. On Earth, gravity distorts the growth of perfect crystals, contaminants float in the air, and the forces of a planet's pull limit what we can manufacture. In the orbital factories adjacent to a cylinder, these constraints vanish. Imagine facilities where pharmaceuticals of impossible purity are crystallized, their molecular structures flawless, leading to more effective medicines with fewer side effects. Picture foundries where metals and ceramics can be mixed evenly and solidified into novel alloys and composites, materials stronger and lighter than anything made on Earth, perfect for the next generation of spacecraft or even the bones of future habitats. One of the most transformative possibilities is in optics and electronics. The ability to grow perfect silicon crystals and deposit thin films in a vacuum could lead to semiconductors and solar panels with efficiencies that dwarf our planetary best. These would not be bulk commodities but high-value, low-mass exports, precisely the kind of goods that justify the cost of shipment across the orbital void. This industrial activity creates the cylinder's economic heartbeat. It provides purpose beyond mere habitation. Scientists, engineers, and specialized technicians would find their skills in high demand, not just for maintenance but for innovation. The revenue from exporting these space-unique products back to Earth or to other developing settlements creates a flow of capital. This capital pays for the constant inflow of specialized resources the habitat cannot yet produce itself, for system upgrades, for cultural imports, and most importantly, for financing the construction of the next cylinder. The initial monumental investment begins to pay dividends, funding its own expansion. This sparks the emergence of a true multi-world economy, built on the principle of comparative advantage. Just as nations on Earth trade based on their unique resources or skills, space settlements would specialize. One cylinder, positioned near a water-rich asteroid, might become the solar system's premier supplier of propellant and life support ice. Another, with a focus on biotech research in controlled gravity, could export advanced medical therapies. A third might dedicate vast internal spaces to artisanal agriculture, growing rare flavors and luxuries impossible in terrestrial soil. They would trade their surpluses, creating a web of mutual dependence that fosters stability and cooperation. The construction industry itself becomes a permanent economic pillar. The shipyards and robotic assembly stations that built the first cylinder do not shut down, they evolve. They become the center of a growing orbital infrastructure sector, building freighters, passenger liners, new habitats, and deep space probes. This cycle transforms the vision from a static colony, a finished product, into a living, breathing, and expanding civilization. It ensures the cylinder is not an end but a beginning. And as this economic engine gains momentum, generating wealth and intertwining the fates of millions living off-world, it inevitably raises profound new questions. Who makes the rules for this new economy? Who resolves disputes between habitats? The very success of the industrial dream forces us to confront the next great frontier, not of engineering or ecology, but of governance and law in a society unmoored from any planetary surface. This new economy demands new rules, a new kind of social contract written for a world without borders in the traditional sense, governing a physically isolated, technologically intensive society presents challenges no earth-bound constitution has ever faced. The stakes are absolute. A major failure in law or leadership could cascade into a life support crisis. So how do you build a government for a bottled world? The models are as varied as human imagination, each with profound implications. One compelling possibility is a hyper-transparent direct democracy. With every citizen connected through advanced networks, major decisions about resource allocation, new construction, or ecological policy could be put to a vote with real-time data on the consequences of each choice displayed for all to see. This system leverages the habitat's greatest strength, its interconnectedness, fostering a deep sense of collective stewardship. The community literally votes on the quality of the air they will breathe next year. Alternatively, the immense cost of construction might lead to corporate-administered habitats where citizenship is tied to employment and governance resembles a blend of a company town and a shareholders' meeting. Rights and privileges could be linked to one's contribution to the maintenance and productivity of the colony. There is also the framework of existing international space law, which designates celestial bodies as the common heritage of humankind. A cylinder might operate under a trustee system, governed by a charter approved by an Earth-based entity like the United Nations, balancing local autonomy with an obligation to the species as a whole. Each model grapples with core questions of sovereignty. Is a cylinder built from asteroid materials and floating in free space its own nation? Does it owe taxes or allegiance to any country on Earth? The relationship with our home planet is a delicate dance. Early settlements will likely depend on Earth for certain high-tech components, specialized medical expertise, and cultural exchange. But as they grow more self-sufficient, the political and economic leverage shifts. Tensions could arise over intellectual property developed in space, or over the environmental impact of diverting asteroids. The clean slate of a new world offers a chance to experiment, to design systems that prioritize long-term survival, scientific truth, and social equity from the very beginning. Philosophers and social scientists might have as much influence as engineers in these early days, crafting bills of rights that include the right to a share of solar energy, the right to transparency from the governing AI, or the responsibility to perform essential ecological service. This is the ultimate weight of the ONeill vision. It is not just about building a place to live, but about building a better way to live together, with the sobering knowledge that in a closed system, every social conflict has an environmental cost. The success of the hardware depends entirely on the wisdom of the software, the laws, customs, and shared values of the people who call it home. And those people, living in an environment of such profound artifice and interdependence, will inevitably develop a culture, an art, and a psychology entirely their own. The resilience of this new society will be tested not by its ambitions, but by its vulnerabilities. Every system, no matter how brilliantly conceived, carries within it the seeds of potential failure. For a world contained within a hull, the most visceral fear is a catastrophic breach. A sizable puncture from a rogue piece of orbital debris or a structural fatigue point giving way would trigger an explosive decompression. The air, the very breath of the colony, would rush out into the vacuum in a matter of minutes. Mitigating this nightmare scenario requires engineering paranoia built into the habitat's DNA. The cylinder would be compartmentalized like a submarine, with massive, automated bulkhead doors ready to slam shut, isolating any compromised section. Beyond redundant hull layers, the entire interior might be enveloped in a secondary, flexible membrane, a giant bag within the shell that could contain a breach long enough for repairs. Every resident would be drilled in emergency response, knowing the location of the nearest personal pressure shelter, a small, reinforced closet with its own air supply, scattered throughout the landscape like lifeboats on a ship. Ecological collapse presents a slower but no less dangerous threat. This meticulously balanced artificial biosphere is a web of dependencies. A pathogen could wipe out a staple crop. A malfunction in the atmospheric processes could allow a dangerous gas to accumulate, or a cascade failure in the water recyclers could poison the supply. The strategy here is diversity and decentralization. Food production would not rely on a single, vast wheat field, but on many separate agricultural modules, each with slightly different cultivars and independent climate controls. Strategic seed banks and genetic libraries would be preserved in hardened vaults. Most importantly, a significant portion of life support would be handled by robust mechanical systems, like electrolysis for oxygen and chemical scrubbers for carbon dioxide, providing a fail-safe that does not depend on the health of a single blade of grass. These systems would have backups for their backups, with enough spare parts and consumables stockpiled to last months or years, creating a deep strategic reserve for the colony. Perhaps the most complex risk is not technical but human. Societal conflict in a closed, high-stakes environment could be devastating. A dispute over resource allocation, a clash of cultural values between different habitat modules, or a simple failure of governance could fracture the community. Mitigation is woven into social design from the start. Transparent, participatory decision-making gives every citizen a stake and a voice. The physical layout itself, with its distinct but interconnected village communities, allows for a degree of local autonomy and cultural expression, preventing a stifling uniformity. Conflict resolution systems would be a core part of civic education, emphasizing mediation and the shared, non-negotiable goal of collective survival. The goal is not to eliminate disagreement, but to engineer a society resilient enough to contain it without tearing itself apart. And then there is the mind. The psychological weight of living inside a world you can see the edges of, under a sky you know is a window, cannot be ignored. The risk of a profound cosmic cabin fever, a sense of claustrophobia or existential disconnect is real. Countermeasures are designed into the landscape itself. Abundant, wild green spaces, gardens that feel untamed, and the constant visual sweep of the interior valley fight the feeling of confinement. Virtual reality portals could offer residents temporary escapes to the beaches of Earth or the imagined landscapes of other worlds, a vital pressure valve for the psyche. Constant, rich connectivity with Earth and other colonies through data streams brimming with art, news, and personal communication maintains a sense of being part of humanity, not adrift from it. This honest appraisal of peril is not a rejection of the vision, but its necessary completion. It underscores that building an ONeill cylinder is not an act of blind optimism, but of profound responsibility. Each potential failure mode is a puzzle to be solved during the design phase, an equation that demands an engineered solution. This pragmatic, problem-solving ethos is what separates a grounded vision from mere fantasy. It demonstrates that the true blueprint for space settlement must include not only the physics of gravity and the biology of soil, but also the sociology of conflict and the architecture of psychological well-being. The cylinder that endures will be the one that planned for its own fragility, transforming every acknowledged risk into another layer of its formidable strength. The blueprints from the 1970s were drawn with slide rules and visionary optimism. Today, we refine them with the cold, precise logic of silicon. The leap from Gerard ONeill's foundational calculations to a buildable design is being bridged by a tool he could only dream of, the supercomputer. Modern computational modeling has transformed the cylinder from a compelling sketch into a virtual prototype we can test, break, and perfect, all within the confines of a server farm. This is where the grand vision meets the granular detail, where we discover if the clouds will form correctly over the interior Alps, or if a microscopic stress fracture could one day unravel the entire world. Fluid dynamics simulations now map the behavior of every molecule in the cylinder's artificial atmosphere. Researchers can model how air will flow across mountain ranges, how temperature gradients will develop between the sunlit windows and the shaded valleys, and crucially, whether the conditions will be right to form gentle, life-giving rain clouds over the farmland. These are not trivial details. They are the difference between a stable climate and a chaotic weather system trapped inside a can. Similarly, finite element analysis software subjects the digital hull to forces that would tear a battleship apart, calculating stresses down to the microscopic level. It reveals where a support rib might fatigue after a century of constant spin and pressure, allowing engineers to reinforce that point before a single piece of metal is ever forged. Even the closed ecological life support system, that delicate web of plants, microbes, and chemistry, is being modeled as a complex adaptive system. Scientists can simulate the introduction of a new crop or the outbreak of a blight, watching how it ripples through the virtual food web and atmospheric balance, allowing them to design greater resilience from the start. This computational revolution is fueled by more than just better software. It is propelled by a changing economic landscape. The vision has been revitalized by organizations like the National Space Society, which continues to advocate and publish detailed studies, and by the seismic shift caused by private aerospace companies. When Gerard ONeill did his work, launching anything into orbit was prohibitively expensive, a barrier owned by governments. Today, companies like SpaceX have fundamentally rewritten that equation with reusable rockets, driving launch costs down by an order of magnitude. This doesn't make building a cylinder cheap, but it makes the initial steps, the deployment of robotic prospectors, the establishment of orbital construction yards, vastly more plausible. It transforms the first phase from a multinational, Apollo-level effort into something potentially within the scope of a sustained public-private partnership. Modern material science adds another layer of feasibility. The advanced carbon composites and nanomaterials we now take for granted in aircraft and sporting goods offer the strength and lightness needed for the hull and structural members, materials that were laboratory curiosities in ONeill's day. Perhaps most importantly, this modern toolkit allows us to interrogate the subtle, second-order effects that the pioneers could only estimate. Take the counter-rotating cylinder pair, the cornerstone of stability. Supercomputer simulations can now model their dynamic behavior with incredible fidelity. How do they handle the slight, uneven distribution of mass as buildings are constructed or a lake is filled? How do they respond to the gravitational tugs of the moon and sun over decades? The models can stress test the control systems, the thrusters and gyros that keep the pair perfectly aimed, ensuring they can handle any foreseeable perturbation. We are no longer just trusting the elegant math of angular momentum cancellation. We are watching it play out in a digital universe, debugging the physics before it becomes a matter of survival. This virtual prototyping phase is the essential, unglamorous work that turns science fiction into engineering reality. It allows us to fail safely and learn exponentially, ensuring that when we finally commit to mining that first asteroid, We are not building a dream, but assembling a machine whose every bolt and breath has been validated 1,000 times over in a world of ones and zeros. This silent, simulated world needs a conductor to bring it to life, orchestrating the construction and daily operation of an ONeill cylinder is a logistical symphony of impossible complexity, with millions of interdependent variables in constant flux. No team of human project managers, no matter how brilliant, could track every robotic miner, optimize every structural weld, and balance the atmospheric chemistry of an entire world in real time. This colossal task will fall to an unseen partner, a vast, distributed artificial intelligence. Think of it not as a single robot, but as the habitat's central nervous system, a pervasive intelligence woven into every sensor, every valve, and every control circuit. During construction, this AI would be the ultimate coordinator. It would manage fleets of autonomous mining drones in the asteroid belt, calculating optimal extraction patterns to maximize yield of needed metals and volatiles. Back at the Orbital shipyard, it would oversee the robotic assembly arms, scheduling the delivery of each prefabricated segment with flawless precision to avoid costly delays, constantly running simulations to predict and prevent potential structural weaknesses before they are built. Once the cylinder is inhabited, the AI's role becomes even more profound, shifting from project manager to life support guardian. It would constantly monitor the breath of the world, analyzing thousands of air samples per second to maintain the perfect balance of oxygen, nitrogen, and carbon dioxide. It would track the flow of every river, the health of every crop in the agricultural bands, and the strain on every critical structural member, making micro adjustments to systems in a continuous, silent dance of maintenance. The level of autonomy required here is staggering. In a crisis, such as a sudden drop in atmospheric pressure or a failure in a primary water recycler, there may be no time for a human committee to debate a response. The AI would need the authority, governed by strict ethical protocols programmed into its core, to execute emergency procedures instantly, sealing bulkheads or rerouting power to backup systems to save the majority. This raises profound questions of trust and governance. How do we encode human values like the sanctity of life and the priority of the community into lines of code that will make life or death decisions? The ethical framework for such an AI would need to be transparent and immutable, a constitution for non-human intelligence focused solely on preserving the habitat and its inhabitants. This deep reliance on smart systems defines the very nature of the civilization that would emerge. The colonists are not mere passengers, they are the partners and overseers of an intelligence that maintains their world. Their culture would be one of symbiosis with technology, where understanding the systems that keep you alive is as fundamental as knowing how to grow food. This civilization is built not just on dreams, but on a foundation of very specific, advanced materials that make such a partnership possible. The silent symphony of this world depends on a physical reality, the very stuff from which it is made. The dream of ONeill cylinders rests not just on brilliant physics or clever software, but on a quiet revolution happening in laboratories today, a quest for materials that defy our current industrial imagination. The hull of a cylinder cannot be ordinary steel or aluminum. It must be a miracle fiber, a substance with the strength of diamond, the lightness of a feather, and the resilience to endure for 1,000 years under relentless cosmic assault. This is the unsung frontier of the vision, where the blueprint meets the periodic table, and where our ambitions are currently held back by the limits of our chemistry. Consider the forces at play. The hull must withstand the outward pressure of the atmosphere, equivalent to an ocean pressing against every square meter, combined with the immense centrifugal stress of its own rotation. On Earth, we build bridges from steel, but the sheer mass of a traditional steel cylinder would make it a gravitational anchor, impossible to spin or maneuver practically. The answer lies in the strength-to-weight ratio, a measure of how much force a material can bear relative to its own mass. Today's cutting-edge carbon fiber composites are a leap forward, but the theoretical holy grail are carbon nanotubes. Imagine a sheet of graphene, a one-atom thick layer of carbon arranged in a hexagonal lattice, rolled into a perfect hollow cylinder a nanometer wide. This structure grants it a theoretical strength hundreds of times greater than steel at a fraction of the weight. A cable woven from such nanotubes could, in theory, form the primary tension members of the habitat's structural skeleton, creating a framework of incredible strength and stunning lightness. Yet here lies the gap between theory and reality. We can create exquisite carbon nanotubes in a lab, but manufacturing them in continuous, flawless strands kilometers long, and at a cost that doesn't rival a nation's gross domestic product, remains a monumental challenge. Researchers are exploring methods from chemical vapor deposition to novel biological templates, racing to scale a technology that currently exists only in grams. Strength alone is not enough. The material must also be a fortress against radiation. While bulk mass is the primary shield, the whole material itself must not become brittle or degrade when bombarded by high-energy particles over decades. This points toward advanced composites, where layers of different materials are fused together. Imagine a hull laminate with an outer layer designed to absorb and disperse the energy of micrometeoroid impacts, a middle layer rich in hydrogen atoms, excellent for stopping neutrons, and an inner layer that provides a final barrier and thermal regulation. Even more visionary are self-healing materials, polymers or composites embedded with microcapsules of liquid resin. If a tiny crack forms from stress or a particle strike, these capsules rupture, releasing a healing agent that flows into the damage and solidifies, automatically repairing the breach before it can grow into a catastrophe. This is not science fiction. Early prototypes exist for terrestrial applications, from airplane wings to smartphone screens, but scaling them to the size of a landscape is a problem of another magnitude entirely. Another promising candidate comes from a surprising state of matter, metallic glass, also known as amorphous metal. Unlike conventional metals, which have an orderly, crystalline atomic structure, metallic glasses are cooled so rapidly their atoms freeze in a disordered, glass-like arrangement. This lack of crystalline grain boundaries makes them exceptionally strong, hard, and resistant to corrosion and wear. They could be ideal for critical moving parts in the central bearing assembly, for gears and joints that must operate flawlessly for centuries without maintenance in a vacuum. The challenge, again, is scale and control. Producing large, uniform batches of these materials without flaws is an active field of research, one where each incremental advance in metallurgy brings the vision of a durable, long-lasting habitat a small step closer. This material science frontier transforms the cylinder from a speculative sketch into a series of feasible specification sheets for future engineers. It provides clear targets, a wish list of properties that laboratories around the world can work toward, even if their immediate goal is a better bicycle frame or a longer-lasting battery. Every breakthrough in bulk nanotube production, every new self-healing polymer formula, every larger ingot of flawless metallic glass is a brick, unseen but essential, in the foundation of a future world. These materials will define the limits of what we can build, how large we can build it, and how safely it can endure. And once we solve the puzzle of the hull, we are confronted with the most complex material of all, the human beings who will live within it, raising the inevitable and profound question of selection. The most advanced material in this entire equation is not carbon fiber or metallic glass, it is human nature, who will be the first to step inside a completed cylinder and call it home. This is not a question of simple volunteerism, but of constructing a founding population as carefully as the habitat itself. The initial crew will be a meticulously chosen microcosm, a complete cross-section of the skills necessary for a society to bootstrap itself. Alongside the obvious engineers, life support technicians, and medical doctors, you will find agronomists who understand closed-loop ecology, teachers prepared to educate the first children born off-world, and artists whose work will help define the soul of this new place. A functioning community needs farmers, cooks, storytellers, and conflict mediators from day one. The selection process becomes a profound filter, looking for a rare blend of technical competence and psychological resilience. Physical health is a baseline, but the deeper criteria are mental and emotional. Candidates must demonstrate exceptional adaptability, a proven ability to cooperate under prolonged stress, and a temperament that thrives in a transparent, interdependent community. Claustrophobia is not an option, but neither is a reckless thirst for frontier adventure. The stakes are too high for individualism. Psychologists would likely screen for traits like conscientiousness, emotional stability, and a strong sense of communal responsibility. The training regimen would be unlike any astronaut program before it. Beyond mastering the technical systems, pioneers would undergo extensive immersion in the cylinder's unique physics. They would live for months in large rotating simulators on Earth, learning to walk, work, and play in artificial gravity, experiencing the Coriolis effect until throwing a ball or pouring a drink feels instinctive. They would train in virtual reality replicas of their future home, memorizing every emergency shelter and backup system, and participate in grueling group simulations of biosphere failures or social conflicts. This preparation aims to make the extraordinary feel routine before they ever leave Earth. Once established, this seed culture will not remain static. It will adapt, mutate, and flourish in its new context. New art forms will emerge, born from the environment itself. Visual artists might work with light projections that dance along the vast, curving interior, or create sculptures that interact with the subtle airflow patterns. Musicians could compose pieces that incorporate the low-frequency hum of the rotating machinery, the habitat's own heartbeat, as a foundational rhythm. Sports would be reinvented entirely. A game of catch becomes a lesson in physics, and team sports would develop with rules that account for the consistent drift caused by the spin. Imagine a form of basketball where the hoop appears to move as you jump, or a new kind of gliding sport that uses the cylinder's gentle air currents. Annual celebrations would naturally tie to the habitat's celestial mechanics, marking not the orbit of a planet, but the completion of its own graceful loop around the sun, a new holiday called Orbit Day. The human capacity for innovation extends beyond survival into the realm of meaning-making. This is the ultimate, unengineerable ingredient. All the perfect systems and robust materials are merely a stage. The play that unfolds upon it, the culture of relationships, rituals, and shared stories, is what will truly transform a breathtaking megastructure from a marvel of engineering into a beloved home. This transformation will not happen overnight, but in a series of distinct generational phases, each with its own challenges and triumphs, building toward a future we are only beginning to envision. A completed cylinder is the destination, but the journey is a story of patient, logical steps. This grandest of projects cannot begin with pouring the foundation for a city in the sky. Instead, it starts with a shovel in the lunar dust or a drill on a captured asteroid. The path from dream to reality will unfold in distinct, overlapping phases, each one a proving ground for the technologies and systems needed for the next. This phased roadmap is the master key, transforming an overwhelming vision into a sequence of manageable, fundable missions. The first phase is not about habitation at all, but about industry. Before we can build a home, we must build the factory that will supply it. Phase 1 focuses entirely on establishing robust, automated mining and processing facilities at our chosen resource sites. Picture a bustling, silent industrial park on the moon's surface, operating under the constant sun. Robotic excavators scrape regolith, feeding it into processing plants that use concentrated sunlight to bake out oxygen and extract metals. The key output of this phase is not luxury, but logistics, the steady, cost-effective flow of raw materials into space. A critical piece of infrastructure here is the lunar mass driver, that electromagnetic railgun that can launch canisters of processed material into orbit with minimal energy. Success in Phase 1 is measured in tons per month, creating the economic foundation that makes everything else possible. With a reliable supply chain established, Phase 2 can begin, the construction of the first true prototype. This would be a small, rotating habitat, perhaps only a few hundred meters long, placed at a stable Lagrange point. It would not be a full biosphere, but a technological testbed and a home for a pioneering crew of maybe 100 people. Its purpose is to answer critical questions in real conditions. Can we maintain perfect artificial gravity for years on end? How do our closed-loop life support systems perform with real humans in the mix? This phase is all about gathering data, debugging systems, and most importantly, building the human expertise needed to operate a world. The crew would be a mix of engineers, life scientists, and specialists, living and working inside the machine they are also learning to maintain. Every hiccup in the atmospheric processes, every unexpected vibration in the structure becomes a priceless lesson that informs the next, larger design. Phase 3 is where the vision begins to take its iconic shape. Using the lessons and materials from the first two phases, construction begins on a full-scale cylinder. Initially, this vast interior will be mostly empty, a skeleton waiting for its flesh. The early focus is on completing the hull, installing the primary life support and power systems, and activating large-scale manufacturing modules within the structure. This cylinder becomes a combination of factory, laboratory, and nascent community. Its population grows into the thousands, but they are not there just to live. They are there to build the economy that will sustain them. This is where those prized microgravity manufactured goods, the flawless crystals and novel alloys, begin rolling off the production lines for export. The revenue generated starts to recoup the immense initial investments and, crucially, funds the transformation of the interior from an industrial space into a living landscape. Soil is imported and laid down, water systems are filled, and the first experimental ecological zones are planted. This phase proves the economic model, demonstrating that the habitat can pay for its own growth. Finally, Phase 4 realizes the complete ONeill vision. The first cylinder is fully terraformed, its interior a mature, stable biome supporting a large, permanent population. More importantly, its twin is constructed, spinning in perfect counter-rotation to provide stability. We now have a paired community, a true island in space. With two cylinders, you achieve not just stability, but the beginnings of a network. They can specialize, trade, and support one another. This is the stage where culture deepens, where children are born who know no other home, and where the complex post-scarcity, adjacent economy we discussed earlier truly emerges. Each of these phases is not just a technical milestone, but an economic stepping stone. The funding model evolves from government-backed research and development in Phase 1, to public-private partnerships for the prototype in Phase 2, to largely private investment driven by the profitable orbital manufacturing of Phase 3, and finally to a self-sustaining, expansion-capable economy in Phase 4. This stepwise approach makes the impossible seem patiently, logically achievable. It is a blueprint not for a miracle, but for a project, the largest project our species has ever contemplated. And as we look beyond that first pair of cylinders, the horizon expands into a constellation of possibilities where the very definition of a civilization is rewritten. The staggering price tag is the first reality any blueprint must confront. We are speaking of investments measured not in billions, but in trillions of dollars, a scale that dwarfs the gross domestic product of most nations. Financing such a dream requires a financial architecture as innovative as the engineering itself, a blend of capital that redefines what is possible. No single entity, not even the wealthiest government, could shoulder this alone. The path forward likely lies in a hybrid model, a tapestry woven from public purpose, private ambition, and global cooperation. One compelling framework is a global consortium, an evolution of the partnership that built the International Space Station. Imagine an alliance of nations, perhaps coordinated through a body like the United Nations Office for Outer Space Affairs, pooling resources, expertise, and risk. Each member contributes what it does best, one nation specializing in robotic mining systems, another in advanced life support, another in heavy launch capacity. This model spreads the financial burden and politically aligns the project with the common heritage of humankind principle, framing the cylinder not as any one country's asset, but as a shared step for our species. Yet the pace of a multinational bureaucracy can be slow, mired in shifting political winds. This is where the dynamism of private enterprise becomes crucial. A second model envisions corporations, perhaps those first established by asteroid mining, funding construction as a long-term business venture. Their initial profits from selling platinum group metals or manufacturing unique materials in zero gravity could be reinvested into building the habitats that will house their workforce and expand their markets. The habitat itself becomes the ultimate company town, but on a cosmic scale, with citizenship potentially linked to contribution. The most speculative, yet fascinating, financial instrument is the issuance of century bonds, debt securities with maturities of 100 years or more. These would be backed not by a government's tax revenue, but by the future economic output of the cylinder itself. Investors would buy these bonds betting that the habitat's industries, from perfect semiconductor crystals to advanced pharmaceuticals, will generate enough wealth over generations to repay the debt with interest. It is a vote of confidence in the long-term viability of a space-based economy, tying Earth's financial markets directly to the success of off-world industry. The dramatic reduction in launch costs driven by reusable rocket technology is the linchpin that makes any of these models more plausible. When launching a kilogram to orbit costs a fraction of what it did just 20 years ago, the business case for in-space manufacturing and construction improves exponentially. It transforms the initial capital outlay from impossible to merely monumental. This leads us to the fundamental question: what is the return on this trillion-dollar investment? The payoff is not measured in quarterly dividends, but in categories that redefine value. Scientific knowledge would accelerate at an unprecedented rate, with permanent laboratories studying fundamental physics, astronomy, and biology in ways impossible on Earth. Resource security for our entire civilization would be enhanced, as accessing the mineral wealth of asteroids alleviates pressure on our planet's finite reserves. Most profoundly, it buys something priceless: species resilience. By establishing a self-sustaining branch of humanity independent of Earth, we ensure that a catastrophe on our home world, whether natural or self-inflicted, does not mean the end of the human story. This is the ultimate business case, one that transcends economics and ventures into the realm of philosophy. It asks us to weigh the cost of steel and silicon against the value of a future for our descendants among the stars. The trillion-dollar investment is ultimately a question of legacy. Constructing these cylinders transcends engineering, becoming a profound philosophical declaration about the future of our species. It is a conscious, deliberate choice to ensure that the story of humanity is not bound to a single world. By dispersing our population into crafted habitats, we build a safeguard, a form of cosmic insurance against the kind of planetary-scale disaster that has reshaped life on Earth in the distant past. This is not about abandoning our home, but about ensuring that no single event, whether a natural asteroid impact or a self-inflicted crisis, can ever be an ending. It is the ultimate act of long-term thinking, stretching our responsibility across generations and light years. This ambition immediately raises complex ethical questions that have no easy answers. If we possess the technology to build new, pristine biospheres in space, what does that mean for our responsibility to the original one here on Earth? The vision posits that moving industry and resource extraction off-world could allow our planetary biosphere to heal and thrive. But this creates a potential moral hazard, a temptation to see Earth as a lost cause or a mere museum while we focus on building anew elsewhere. The ethical path forward demands that space settlement be paired with a renewed commitment to planetary stewardship, viewing the two not as opposing choices, but as complementary strands of the same goal, preserving the thread of life in all its forms. The question of access and governance is equally fraught. Who gets to go? Who makes the rules in these new worlds? If the first habitats are built through immense private investment or by a consortium of wealthy nations, does that risk creating a cosmic caste system where the future is owned by a select few? The principles of equity and the common heritage of humankind, often cited in space law, suggest that these new frontiers should be open to all of humanity. Yet the practical realities of selection, as we discussed, are intensely selective. Navigating this tension requires designing systems from the start that are transparent and fair, perhaps with lotteries for residency, cultural exchange programs, and governance models that include voices from across Earth. The goal must be to avoid replicating the old patterns of exclusion and colonization in this new context. Living inside a world of our own making forces a fundamental re-examination of what it means to be human. For the first time, our environment is not a given, not a gift of nature, but a product of our intellect and will. The weather, the length of the day, the very soil underfoot are all design choices. This total mastery could lead to a profound shift in consciousness, from seeing ourselves as inhabitants of a world to being its stewards and co-authors. Every ecological balance becomes a conscious responsibility, every social harmony a deliberate achievement. This might foster a deeper, more visceral understanding of interconnection, or it could create a strange existential tension, a longing for a wildness and mystery that no designed park can fully replicate. Taking this step irrevocably redefines our place in the cosmos. We would transition from a planetary species to a spacefaring civilization. Earth becomes our cradle, our place of origin, but not our only home. This perspective, often called the overview effect by astronauts who see Earth from orbit, would be magnified 1,000-fold. Seeing our home planet as a fragile blue marble from the window of a self-built world could instill a powerful, species-wide sense of unity and care for it. At the same time, our horizons would expand immeasurably. The solar system and eventually the stars would become not just destinations for exploration, but potential real estate for new branches of human culture to grow in their own unique directions. This vision inevitably draws comparisons to other grand concepts for humanity's future, from domed cities on Mars to hypothetical megastructures like a Dyson sphere. Each offers a different answer to the same fundamental urge. Mars settlement represents a return to a planetary surface, with all the familiar challenges of gravity wells and limited space. A Dyson sphere is an energy-harvesting project of almost inconceivable scale, focused on capturing a star's total output. The ONeill cylinder sits between these poles, a habitat focused first and foremost on creating an ideal, scalable home for life itself. It is not about conquering a hostile world or harnessing a star. but about carefully crafting a place where human and ecological flourishing is the primary design spec. In that choice, it makes its quietest, most powerful statement that the future is not something we find, but something we build with intention for life. The debate between building new worlds and settling old ones is one of the most defining conversations for our future. On one side of this cosmic discussion stands the red planet, Mars, a destination that has captured our imagination for centuries. On the other side are the ONeill cylinders, a vision of manufactured homes in the void. Each path offers a radically different answer to the same fundamental question: where should humanity plant its next roots? Mars presents itself as a ready-made, if hostile, foundation. It is a whole world with vast resources, from water ice at its poles to minerals in its soil. There is a tangible, fixed surface to build upon, a connection to the deep history of our solar system that appeals to our explorer's spirit. The journey to get there, while long, is a straight shot to a known destination. Yet the Martian environment is unforgiving in ways that demand constant, energy-intensive struggle. Its gravity is only 38% of Earth's, a force too weak to hold a substantial atmosphere, and whose long-term effects on human health, especially for children born there, remain a profound unknown. The thin air offers little protection from radiation and cannot support liquid water or unpressurized life. Every human activity on Mars would occur inside sealed habitats or bulky suits, with the entire civilization perpetually one mechanical failure away from catastrophe. Terraforming Mars into an Earth-like world is a dream spanning millennia, requiring technologies that border on planetary-scale geoengineering, from melting polar caps to creating an artificial magnetic field. It is the path of the planetary gardener, attempting to nurse a distant, cold world back to life. The philosophy of the ONeill cylinder is fundamentally different. It accepts that a perfect Earth-like environment cannot be found, so it must be built. Instead of adapting humanity to a harsh planet, it adapts the habitat to humanity's needs. The cylinder offers a complete package from day one: Earth normal gravity, a breathable atmosphere, a controlled climate, and protection from radiation through sheer mass and design. Its location in free space, likely within the Earth-Moon system, offers a crucial logistical advantage: proximity. Travel and communication times are measured in days, not months, enabling robust trade, cultural exchange, and emergency support from Earth. This closeness fosters a sustainable economic loop, where cylinders can export high-value manufactured goods and import specialized goods from Earth, growing an integrated orbital economy. The trade-off, of course, is the sheer magnitude of the construction project. A Mars settlement, for all its difficulties, begins with a single landed module. An ONeill cylinder requires a fully built and sealed world before the first resident can move in, a prerequisite of staggering complexity and upfront cost. It represents the philosophy of the architect, believing we can design a better foundation than nature has left for us in our immediate neighborhood. This is not a contest with a single winner, but a spectrum of complementary strategies. Mars settlement is a monumental challenge of adaptation and endurance, a test of our ability to survive on another planet's terms. The ONeill vision is a challenge of creation and integration, a test of our ability to build new terms entirely and maintain a deep connection to our home planet. They can and likely will coexist. Early Martian outposts might be supplied by industries based in orbital habitats, which process asteroid materials into fuel and building supplies. In return, Mars could offer a unique planetary environment for certain types of research or resource extraction that benefit the growing orbital civilization. Understanding this debate clarifies that ONeill's blueprint is not a rejection of planetary exploration, but a parallel vision for where the bulk of humanity might ultimately thrive. It suggests that the true seat of a spacefaring civilization may not be on the surface of alien worlds, but in the spaces between them, in crafted environments where the conditions for life are not a lucky accident, but a deliberate achievement. This powerful idea of building our own worlds has, perhaps unsurprisingly, escaped the pages of scientific journals to find a permanent home in the stories we tell ourselves, shaping how generations have envisioned life beyond Earth. The blueprints have leaped from academic papers to the silver screen, becoming a familiar backdrop for humanity's future. In the world of Mobile Suit Gundam, the sprawling, conflict-ridden space colonies are directly modeled on Gerard O'Neill's Island 3-cylinder design. These are not mere set pieces, they are characters in their own right, complete with bustling cities, artificial weather, and the political tensions of enclosed societies. This depiction did something remarkable. It presented life inside a rotating habitat not as a sterile laboratory, but as a lived-in, complex reality for millions. It normalized the idea, making the cylinder a plausible setting for human drama on an epic scale. Decades later, the film Interstellar offered a quieter, more hopeful vision. The final act reveals a fleet of massive ONeill cylinders slowly rotating near Saturn, each cradling small towns, forests, and farmland under strips of simulated sky. This portrayal emphasized the cylinders as arcs, humanity's gentle answer to a planetary crisis, focusing on preservation and continuity rather than conflict. The aesthetic was one of serene, pastoral beauty, a stark contrast to the dying Earth left behind, framing the cylinders as sanctuaries. More recently, the television series The Expanse presented perhaps the most grounded and politically charged version. Here, the cylinders are the beating heart of the belt, the asteroid belt's population. Places like Ceres Station, while carved from an asteroid, operate on the same rotational principles, and the sprawling, class-divided interior of the generation ship Novu is a classic ONeill design. The series excels at showing the gritty, lived-in mechanics of such a world, from the Coriolis effect on poured drinks to the social stratification between those who live on the slower spinning docks and the faster spinning residential levels. It explores the physical and sociological realities, the dependence on complex life support, and the vulnerability of a society whose entire existence is contained. This gritty realism makes the concept feel tangible, immediate, and fraught with both wonder and peril. This cultural footprint is a powerful feedback loop. Science fiction does not just reflect scientific ideas, it actively shapes them. A teenager watching Gundam or The Expanse is not just being entertained, they are being subconsciously educated. The cylinder ceases to be an abstract diagram in a physics textbook. It becomes a place where people fall in love, argue over politics, and dream of the future. This normalization is invaluable. It generates public fascination, which in turn fuels support for space research and inspires that next generation of aerospace engineers, material scientists, and ecological designers. Many professionals in the field today cite early exposure to such vivid, thoughtful science fiction as the spark that ignited their career path. The fiction provides the emotional and narrative context that raw engineering specs cannot, answering the subtle but vital question of why we would undertake such a monumental task. It paints the destination in human colors. This interplay between imagination and calculation is the engine of progress. The dream, kept alive and evolving in our stories, creates a cultural readiness, a sense that this future is not only possible but somehow inevitable. That cultural momentum is precisely what allows visionaries to secure funding for the first small steps, turning cinematic spectacle into laboratory prototypes and, eventually, industrial plans. The fiction makes the impossible feel familiar, and that familiarity is the first crucial step toward making it real. The headlines of today are quietly assembling the toolkit for tomorrow's worlds. While no full-scale cylinder yet spins in the void, its foundational technologies are being prototyped and proven in laboratories, on the International Space Station and in the business plans of daring startups. This is not science fiction deferred, it is engineering in its earliest, most crucial phase. Consider the breadth of a future habitat. For years, NASA has been meticulously researching closed-loop life support systems, aiming to recycle nearly 100% of water and air. Experiments aboard the space station have successfully grown lettuce and other crops, not just for science, but to understand how plants function as integral parts of a life support machine, scrubbing carbon dioxide, generating oxygen, and providing fresh food. Each successful harvest is a small step toward the vast agricultural bands of an ONeill cylinder. The water recycling systems on the station, which purify and reuse every drop from sweat, shower runoff, and even urine, are direct precursors to the intricate hydrological cycles that will sustain a space-bound valley. These are not abstract studies, they are survival technologies being debugged in real time, 400 kilometers above our heads. The quest for materials is also moving from theory to practice. Private companies are taking the first tangible steps into the resource economy that will supply those materials. A firm called Astroforge has launched demonstration missions to test the technology for prospecting and processing asteroid-like materials. Their goal is to identify and eventually extract precious metals from space rocks. While their initial focus is on creating a new market for platinum group metals on Earth, the technology they pioneer, the autonomous spacecraft, the spectroscopic analyzers, the methods for handling material in microgravity, are the exact same tools that will one day feed raw ore into the orbital factories that build habitats. They are proving that in-situ resource utilization is a viable business model, not just a theoretical chapter in a 50-year-old book. Even the dream of boundless solar power is gaining concrete form. Research into space-based solar power, once a fringe idea, is receiving serious attention from agencies in Europe, Japan, and the United States. The concept involves constructing vast arrays of solar panels in orbit, where they can capture sunlight uninterrupted, and beaming the energy wirelessly to Earth as microwaves or lasers. The engineering challenges of wireless power transmission and building gigantic structures in space are immense, but the underlying work on ultra-lightweight solar cells, precise beam control, and orbital assembly directly informs the technology needed to build the enormous solar mirrors and power grids for a cylinder. Each breakthrough in efficiency brings the energy-rich future of a space settlement closer to reality. Perhaps the most symbolic stepping stone is the renewed focus on artificial gravity itself. For decades, human spaceflight has accepted the debilitating effects of weightlessness as a necessary evil, mitigated by intense exercise regimens. But a growing consensus acknowledges that for permanent settlement, we must solve the gravity problem. This has sparked new designs for smaller-scale demonstrators. Organizations like the Gateway Foundation have published detailed concepts for a rotating space station called the Von Braun, a wheel-like structure designed to provide partial gravity through rotation, serving as a hotel and research center. While still a concept, it represents a critical shift in thinking, moving artificial gravity from a textbook principle to a stated design requirement for future human habitats. NASA and other agencies are now funding studies on the physiological effects of different gravity levels, research that will determine the optimal spin rate and diameter for the first true space homes. These disparate projects, from botany experiments to asteroid prospectors, form a scattered but unmistakable mosaic. They are the individual brushstrokes of a much larger picture. No single government or company is building a cylinder, but collectively, they are solving every major subsystem required to do so. The journey has unequivocally begun, not with a thunderous announcement, but through the incremental, persistent work of scientists, engineers, and entrepreneurs who looked at Gerard ONeill's blueprint and asked a very practical question: what is the very first thing we need to learn how to do? Each answered in their own way, and together they are turning a visionary's dream into a series of solvable engineering problems, one patent, one prototype, one successful test at a time. The final destination of this blueprint is not a single point in space, but a new state of being for our species. A successful cylinder at the Lagrange point proves the concept, demonstrating that we can build stable, self-sufficient homes in the void. From that first foothold, the vision expands exponentially, not across planetary surfaces, but through the empty spaces between them. Imagine, centuries from now, similar constellations of habitats established in orbit around Mars, providing comfortable bases for those who work on the red planet's surface. Picture vast, slow-moving arcs constructed in the resource-rich asteroid belt, each a thriving metropolis fed by the mineral wealth all around it. The ultimate promise is that we are not limited to this solar system. These self-contained worlds could become our generation ships. A cylinder, with its balanced ecology and artificial sun, could be accelerated over centuries to cruise between the stars, carrying a complete human culture and biosphere within its hull. Upon arrival at a new star, it would not need to search for a perfect planet. It could simply park in a stable orbit, a ready-made home, and begin building more. The galaxy becomes not a search for a new Earth, but a canvas for building new homes. This transforms our understanding of what it means to be a spacefaring civilization. We are no longer explorers hoping to stumble upon a place that can tolerate us. We become builders, carrying the conditions for life with us. This long-term vision weaves every previous discussion into a single, breathtaking tapestry. The rotational physics, the radiation shielding, the closed-loop ecology, and the novel social structures are not just solutions to isolated problems. They are the foundational skills of a new kind of society, one whose purpose is to create and nurture life in the cosmic dark. The immense upfront cost and staggering engineering become investments in a capability, the ability to make any point in space hospitable. The economic models we invent to pay for the first cylinder become the templates for an interstellar economy of ideas, culture, and unique goods traded across light years. The governance experiments within those first habitats become the cultural seeds for branches of humanity that may evolve in wildly different directions, united by their common origin as world builders. It is a vision that redefines our cosmic destiny. For millennia, we have looked at the stars and wondered if we are alone. This path suggests a different answer. We may ensure we are not alone by filling the quiet neighborhoods of our galaxy with the light of our own creations. We become the gardeners of the vacuum, planting islands of life around star after star. This is the profound legacy of Gerard ONeill's question to his students. It was never just about solving an engineering problem. It was about offering a hopeful answer to the deepest of human anxieties, the fear of having all our eggs in one planetary basket. It provides a practical, step-by-step pathway from where we are today to a future of almost unimaginable resilience and diversity for our species. The cylinder is more than a habitat. It is a philosophy made manifest, a declaration that humanity's true home is not a place, but a skill, the skill of crafting a world. And with that skill mastered, the universe itself becomes our neighborhood. This journey from a classroom question to a blueprint for stars reveals a profound truth about our species. We are not defined by the world we were born on, but by the worlds we can imagine and build. The ONeill cylinder is more than a megastructure. It is a manifesto, a declaration that humanity's next evolutionary step is not to adapt to the cosmos, but to thoughtfully rearrange its pieces into new homes. We have navigated the physics of spinning gravity, the ecology of sealed biospheres, and the sociology of bottle world communities. Each challenge underscores that this is not a sudden leap, but a patient, logical procession of problems we are already learning to solve. The vision merges our deepest instincts, the drive to ensure our children's future, the curiosity to push boundaries, and the creative spark to design beauty from raw mechanics. It suggests our destiny is not to be mere visitors on other planets, but to become gardeners of the vacuum, cultivating life in crafted valleys under artificial suns. This path offers a quiet answer to an ancient fear, the vulnerability of having all of existence confined to one fragile sphere. By learning to build our own arcs, we weave a safety net for life itself, ensuring that no single event can ever be a final period in the human story. The work has already begun in orbital laboratories and asteroid prospector business plans, each a small, vital piece of a puzzle spanning generations. As we look up at the night sky, it is no longer just a field of distant points of light. It becomes a neighborhood of possibilities, waiting for the light of our own creations to join them. If this vision of a future built among the stars resonates with you, we would love to hear your perspective. What aspect of building a space habitat excites you the most, or what challenge gives you pause? Share your thoughts in the comments below and subscribe for more journeys into the architecture of tomorrow.